RTL SDR modules are incredibly popular due to their low cost and versatility. However, if you're doing something that requires a high degree of frequency precision, the temperature stability of the internal 28.8 MHz oscillator that comes with these things may not be sufficient for your needs. So it's very common to see people replace this with a 28.8 MHz temperature compensated oscillator module like one of these. Now, this is not a 28.8 MHz oscillator because unfortunately it's very difficult to find 28.8 MHz oscillator modules. It's not a very common frequency, especially if you're looking for one that's temperature compensated and has low drift over temperature. So if we can't buy one, we'll just have to build one. Now, if we want 28.8 MHz and we can't use a 28.8 MHz oscillator because we can't find them, then there are a couple options available. I've seen people use a 14.4 MHz oscillator along with a RF mixer, which they use to multiply these frequency by 2 in order to get 28.8 MHz. I don't particularly like this option simply because a good RF mixer can cost easily as much as the RTL SDR itself, and to be honest, 14.4 MHz is still not that common of a frequency. Easier to find than 28.8, but still can be a bit difficult to source. So I think I'm going to go with 19.2 MHz as my base oscillator frequency. Now, 19.2 MHz may be a very popular frequency, but I know what you're thinking. There's no integer multiple of 19.2 that will give us 28.8. That's okay. We're going to do a little trick here. If we take 19.2 MHz and we divide it by 2, that gives us 9.6 MHz. And it just so happens that the third harmonic of 9.6 MHz is 28.8 MHz. So all we need to do is add a filter to filter out the third harmonic of our 9.6 MHz signal, and we'll get 28.8 MHz. So assuming we can get a stable 19.2 MHz oscillator, the next thing we need to do is implement a divide by 2 circuit. And that's very easy. All we need is a single D-type flip-flop. And I've talked about this in more detail in a previous video, but a simple single D-type flip-flop, if you input a signal to the clock, connect the data to the inverting Q pin, and take your output from the Q pin, will give you a divide by 2 circuit. So our input frequency of 19.2 MHz will get divided by 2, and the output will be 9.6 MHz. It will also be a square wave since this is a logic gate. And so that means it's going to have some pretty nice, strong harmonic content, which is good because we want to have as strong of a third harmonic as possible because we're going to need a filter to filter that out. Now the filter itself is a little more complicated. We need a bandpass filter because we not only want to knock out the higher order harmonics such as the 5th and 7th harmonic, but also that fundamental 9.6 MHz signal as well. So this is a third order Butterworth bandpass filter, and I just used a little design program to design it and adjusted the capacitors for standard values. And the inductors, we only need 3 of them, and they need to each be 425 nanohenries. So let's go build this up on the bench and see how it performs. So here is the bandpass filter in all its glory. Now I've just, again, got some standard value capacitors in here. These are all NPO type. You don't want to use cheap ceramics here. They typically will not be very stable. And for each of the inductors, I've just wound 9 turns around a T50-6 toroid core. As for the filter's performance, well, I'm pretty happy with it. It has a fairly low insertion loss here at 28.8 MHz. And we can see that the cutoff as we get down towards 9.6 MHz is very steep. So that fundamental should be knocked out really well. And although the cutoff above our bandpass is not as steep, it's still good enough so that even at the 4th harmonic at 38.4 MHz, we should knock that down by better than 40 dB. So I think this will work really well for filtering out that third order harmonic at 28.8 MHz. So I have my function generator outputting a 9.6 MHz square wave. We can see the fundamental here at 9.6 MHz is just about 0 dB. The third harmonic at 28.8 MHz is about negative 16.5 dB here. And if I insert that filter, the fundamental and all of that other harmonic content just disappears. So with the filter taken care of, all we need now is a 19.2 megahertz oscillator. Now we could get a 9.6 megahertz oscillator, and then we wouldn't need to divide the frequency by 2 here, but like 28.8 megahertz, 9.8 megahertz is a fairly uncommon frequency. 19.2 megahertz, on the other hand, is incredibly common. In fact, there is no shortage of temperature-compensated, inexpensive oscillator modules you could buy and just drop right in here and be done with it. But sometimes it's more fun to build your own. Now this is a classic Pierce gate oscillator based around a 10 ppm 19.2 megahertz crystal. And I've already done a whole video on Pierce oscillator design and how they work, so I won't go into too much detail on this. But the basic idea is you have a inverter gate that's biased into its linear region through this resistor, and then you have your feedback network with the crystal in it. And this second inverter gate is simply an output buffer. And if this circuit looks familiar, well, it's exactly the same circuit that I used in my previous video on oscillator simulation and design. And if you'll recall from that video, this oscillator, as is, had pretty reasonable temperature stability from 20 degrees Celsius up through about 65 degrees Celsius. There was a maximum frequency deviation of about just a little over 70 hertz. Now at 19.2 megahertz, that translates to just under 4 parts per million. But we can improve on this. Now whenever you buy a crystal off of Mouser or DigiKey, they're almost certainly an AT cut crystal. And AT cut crystals have a cubic frequency versus temperature curve. So you can see here as the temperature increases from room temperature, then the frequency will typically decrease. And likewise, as the temperature decreases from room temperature, the frequency will increase up to a point. So they each have a turnover point here, and at that turnover point is where the frequency reverts. So as temperature decreases, you will increase in frequency up to the turnover point, and then you start decreasing in frequency again. Likewise, as temperature increases, you'll typically decrease in frequency up to the turnover point, and then you'll start increasing in frequency again. Now you can get into some fairly complex compensation techniques if you want to compensate over this entire frequency range, but if you're only concerned with compensating between the two turnover points, which typically constitutes the normal range of operation for most people, then it actually is pretty simple. We can do it with a single capacitor. Going back to our oscillator, you can see that I have this trim cap here in series with the crystal. And that's just there so you can slightly adjust the crystal frequency to be exactly on 19.2 megahertz. So the lower this capacitance is, the higher in frequency the crystal will oscillate. And the higher this capacitance is, the lower in frequency the crystal will oscillate. Now, all of these capacitors are NPO types, so they don't change much with temperature. But what if we added a capacitor that intentionally had a negative temperature coefficient? Now I've added a second trimmer capacitor here in parallel with the first, only this one is not an NPO type, it's an N750, which means it has a negative temperature coefficient. So as the temperature increases, the crystal is going to start oscillating at a lower and lower frequency. However, this capacitor, as the temperature increases, will decrease in capacitance. That means that the crystal will see a smaller and smaller capacitive load, and that will tend to counteract the crystal's natural frequency drift, because as this capacitance is lowered, the crystal will be forced to oscillate at a higher frequency. And likewise, as the temperature decreases from room temperature, this capacitor, of course, being a negative temperature coefficient capacitor, will increase in capacitance, and that will counteract the crystal's natural tendency to raise its frequency as the temperature is lowered. Now, of course, this will only really work in between the crystal's two turnover points here, because once the crystal hits its turnover point, as the temperature increases, it'll start actually increasing in frequency, and so that capacitance will continue decreasing, which will just exacerbate this upwards portion of the curve. Same thing with the lower temperatures as well. But between these two turnover points, we can actually flatten this out significantly. Now, if you look inside here, you can see my two trim caps, and they are in parallel as we saw in the schematic. The black one is the NPO type, and the red one is the N750. Now, since they're in parallel, you can trim them so that they have different ratios. And that will help you control how much effect the N750 has on the actual frequency. So for example, if the N750 is very small and the NPO is larger, then obviously the N750, as it changes with temperature, will have less of an effect on the frequency, and vice versa. So I was expecting to kind of have to fiddle with at least a couple of times to get a decent frequency response, but it turns out whatever values these two are set to, I lucked out with because they actually have a pretty good response as is. So with that temperature compensation capacitor in there, I stuck it in the oven and ran it from 20 degrees Celsius up through 60 degrees Celsius. And you can see that until we hit that turnover point here, right around 55 degrees, we actually had very little frequency deviation. In fact, the maximum was at about negative 21 hertz. That's less than 1 part per million at 28.8 megahertz, which is really, really good. Now, obviously, yeah, once we hit that turnover point, the capacitor just exacerbated that upwards curve and it just shot up through the roof. But we fully expected that. Now, unfortunately, I don't have a really well-controlled method of testing these things at lower frequencies. I don't have a controlled fridge or anything like that. So I just got really just 2 data points here, which is why below 20 degrees you kind of see it shoot up and then shoot down here. The first data point here was just for me sticking the oscillator in a bowl of ice for 30 minutes. And that got it down to about 5 degrees Celsius. And you can see it, the frequency rose up by about 20 hertz here. So then I opened up the case and hit it with a good shot of freeze spray. And that dropped the temperature down to about negative 5 degrees here. And you can see that brought us down to about negative 45, negative 50 hertz below our nominal frequency. So that's not a terribly great spec. That's worse than 1 part per million. But if you look here at 0 degrees, you can see we didn't even drop really by negative 20 hertz even. So between 0 degrees and 55 degrees or so, we easily are within plus or minus 1 part per million with this temperature compensated oscillator, which it's not a great spec if you were to buy a temperature compensated oscillator that was commercially manufactured, but considering we're doing this with just a single capacitor, that's pretty darn good. So I think most people would probably just buy a temperature compensated oscillator here, and it would certainly have a much better performance over a wider temperature range. But it's surprising how well a simple capacitive temperature compensation scheme can work. And of course the rest of the circuit is incredibly simple, just a flip-flop and our filter. And I have added a couple of resistors here to give it a reasonable 50 ohm termination at both the source and the load, and that's really all there is to it. And as you might expect, with that filter in place, we get a nice clean sinusoid here at 28.8 megahertz. Now, the amplitude is a bit low here. We're getting about a little over 600 millivolts peak to peak, and that's because we're dealing with the third harmonic, which of course is going to be smaller in amplitude than the fundamental. We also have some losses in the filter itself, and because the filter is 50 ohm terminated at both its source and its load, we have a bit of voltage division going on there as well. But 600 millivolts peak to peak should be enough for what we need. Because according to the data sheet for the R820, which is the chip that my RTL SDR uses, the input level when using an external clock needs to be between 120 millivolts peak to peak and 3.3 volts peak to peak. So we should be right in that range. However, when I naively connected the oscillator to the crystal input pin, nothing happened. Now, I did play around with this a bit, and I found if I put in a large amplitude signal into the crystal input pin, then everything worked fine, but otherwise it wouldn't even show up as a USB device, so it clearly was not getting a clock signal. And I went back and took a closer look at the datasheet because we are within spec here in terms of the amplitude of our signal. However, if you look closely, it says the input level to extal_P pin. Well, there is no extal_P pin here. There's only extal_I, which is the input, and extal_O, which is labeled as the output. I was like, well, maybe they just mislabeled this somehow. And if you look over here, there is an IF_P, and that is defined as the intermediate frequency output pin. So I think what happened is they just transposed their suffixes here, and they meant to put extal_O, but did _P instead. And sure enough, when I stuck my 600 millivolt peak-to-peak clock signal into extal O, everything worked fine. Now, as for actually interfacing with the dongle, I of course had to remove the 28.8 megahertz crystal that was here. And if you flip over on the back, I tacked on a BNC connector. There was a convenient little ground pad here I could ground the BNC connector to. And then the center pin I just jumpered over to the external out pin. So it may look a bit Frankenstein-y, but it does work. So I'd still like to do a little more work on this just to optimize it for size so it's not quite so bulky, and for power so it can run off 3 volts instead of 5. But as a prototype, it works quite nicely. And I'll link in the schematic and project files in the video description for anyone interested. And as always, if you have any questions, suggestions, or corrections, be sure to leave them in the comment section below. Thanks for watching.